So how do we do this in R? I'm going to make a separate video that shows how to do this in Python, but for the purpose of this lecture, let's do it in R. In order to do it in R, you're going to need to install the survival package if you haven't done so already. And we can read in this data set. It's called the service 1 year data set. If you don't want to do that and just want to type it directly, here's how you can type it in directly. There's a function called servFit that fits these basic life tables Kaplan-Meier estimators. The dependent variable is going to be the time of either censoring or cancellation. So big T indicates the time of censoring or cancellation. And then this serve thing also has an indicator that indicates if the event occurred. So different software expect a different indicator. In R, it's always that the event occurred. So I have a variable cancel that indicates whether or not the customer canceled. So they say some software wants to know whether or not the customer was censored, and that's slightly confusing. So I want to describe this as a function of just an intercept, if you will. We're not going to break this out by any other variable, and that's why we have a tilde1. So think of this as like the intercept model. I'm going to weight by these counts, since I have aggregated data here. I've given counts as I had in this table, so a very concise way. The alternative would be to have 671 rows in the data set, and that's probably what you'd be more likely to encounter if you were doing this with a real database for a company. But I've already done substantial aggregation to end up with these counts. If you do a summary on this fitted object, what you end up with is something that looks a lot like the table that we worked through together a couple slides ago. So we had the number at risk, we had the retention rates in the survivor function. Summary function gives us the number at risk, the number of events. So think of this as the number of flips, the number of heads. Here's your survival function. And it actually computes a standard error for us with a confidence interval. If you plot a fitted object, you get the survivor function, which looks a lot like the one that I created by hand back here. So we saw a substantial drop. Here we see a step function with a pretty substantial drop at month 7 and smaller drops for the other months. Now we could compare this with what we get with the simple retention model. So this was the formula that we had. Take the number of cancels, divide by the number of flips, subtract that from 1, and you have the retention rate. So here's my R code to do that. If I take the sum of my t values times the counts, we end up with the number of flips. Here's the number of cancels. 1 minus that gives us the retention rate. I'd now like to work a slightly more complicated example. It turns out I had more than 1 year, but for the initial example, I wanted to keep it 1 year because it would all fit on one page. They actually gave us 5 years of data, though, when we did this project for the company. There's another data set out there called Service 5 Year. And if you bring that in, what you will see is, and I can fit the same survivor function as I had before on the 5-year data. Now, if we go look at our hazard function, remember the hazard is telling me when is this event cancellation likely to occur. What we see are regular spikes at, it appears to be 7 and 13, and then another 6 months out, another 6 months out. And it's almost like there's something going on at, something after month 6 and after month 12, and every, multiple of 6 that we need to worry about. And it turns out there's another variable in the data set that we should have been accounting for, and that is the length of the initial contract. So at this company, you sign up either for a 1-month contract, so month-by-month contract, or you get a little price discount if you sign up for 6 months at a time, or if you really like them, you can sign up for a 12-month contract. And so maybe these spikes are really capturing this variable that should have been included in the analysis, which is the length of your contract. Now, before we account for that, I want to make a really important point. So here's the survivor function versus the survival function using the simple retention model. Now, when we look at the hazard function, this hazard function looks absolutely nothing like the simple retention hazard function. But when we look at the survivor function, the two look almost identical. One is a little bit above the other, then it goes a little bit below, but the two are really close to each other. And if you remember, the way we can compute lifetime value is to multiply the survival function times these m sub t's. Now, if my survival functions are roughly the same, then the lifetime values will also be roughly the same, whether I use the more complicated general retention model or if I just use the simple retention model. I think this is a kind of a profound point that the simple retention model makes a very unrealistic assumption that's probably not at all plausible in most cases. However, when it comes to computing lifetime value, it's going to come relatively close because what's happening is these retention rates are kind of averaged, and once you average them, you get something like what you have with the simple retention model. Despite the fact that we made very unrealistic assumptions, the simple retention model will get you in the ballpark, and I tend to use it very often because it's so easy to explain to people, even though it makes some pretty unrealistic assumptions. What comes out is pretty good. So the next thing I did was to compute lifetime value using the fancy generalized retention model with survival analysis estimates versus the simple retention model estimates. Now, SRM takes this out to infinity, whereas the GRM can only take it out 5 years. So to make this comparable, I've only taken the SRM out 60 months or 5 years. And so I've computed the survivor functions with both using this formula that we had here. I've computed the products of m sub t times these survival functions. I've added them up, and what we see is that using the correct general retention model, we come up with $424 as the lifetime value. With the simple retention model, we overestimate it by a little bit, but it's in the ballpark. By the way, this is assuming a period cash flow of $23.20, which was the actual amount minus some cost of goods sold, converting yen to dollars. So it was, kind of a complicated calculation. To compute this sum in R, all I do is I take the fitted survival function times, here's my m sub t's. So it's a one-liner in R to get to this number. And so again, what I'm doing is I'm just computing that same formula. Another thing that we can do is account for the fact that different customers sign up for different initial contract lengths. So this is, think of it as a static covariate. I know this at the beginning of the life of the customer. You either sign up for 1 month, 6 month, or 12-month periods. Now maybe you change that along the way, but I'm not going to account for that. That would be a time-dependent covariate. We'll deal with that next week. So the way you can break it out by some discrete covariate, if you will, is with, instead of saying tilde1, you say tilde start length. And this is going to stratify your survival analysis by this starting length. So now I end up with different survival functions depending on the length of the initial contract period. And so it's kind of interesting to compare these. The solid line shows those who were on the 1-month contracts. And what you see is that there's a fairly high hazard rate at first, but then it declines over time. So it's very common to see that declining hazard function the longer you've been a customer. The pattern for 6-month, though, is quite different. So you get a spike after 6 months, then after 12, after 18, after 24, and so forth. Whereas those on 12-month contracts tend to stay in 12-month contracts. You get a spike after 12, 24, 36, but you don't get a spike here at 6 months, 18 months, 30 months, and so forth. I think the survivor function may be even clearer, where you do a much better job of holding on to the 12-month people, and then as soon as month 12 hits, the floor drops out. Then you do a better job of holding on to them, and then the floor drops out. Whereas you get a pretty steady declining function, survivor function, for the 1-monthers, and the 6 months are somewhere in between. The other thing that's very obvious from this plot is even after a long period of time, the 12-month customers are better. A higher fraction are surviving than with the 1-month contract people. We can further break this out by contract length. You can see that even with the 1-month contract length, the hazard function is not constant. You have a much higher churn probability at the beginning that declines the longer a customer has been with you, the more loyal that customer becomes. Despite that, the survivor functions are about the same, so your lifetime value estimates should be pretty similar. You could look at it for the 12s. The 12s have a radically different hazard function using the general retention model versus the simple retention model. Here the survivor functions differ a bit more. We can go compare these estimates, though, across them. And you can see even with this extreme 12-month case where the general and the simple retention models produced very different survival and hazard plots, the lifetime value estimates are pretty similar. So 571 versus 576. So again, the point is you can do quite well using the simple retention model, but I think you get much more understanding from looking at these hazard plots.